Hello, Dr. Schreifels here today. I know some students in taking general chemistry have, in second semester, learn about acids and bases, and one common topic that people discuss and learn is common ion effect, which involves either acid or base. So here's an example problem that I know students have encountered and didn't quite know how to work. So you have a solution that contains nominally 0.1628 molar ammonia and also 0.1362 molar cesium hydroxide. The overall reaction is this. So you notice this is a strong base, and this is a weak base. So two bases in there, and so you're left with, how do I solve this? Well, you note that you're trying to get ammonium ion, which is a product. So if we think about what this means, it means that we have two products that are on the right side, and hydroxide can come from the equilibrium here, where ammonia splits apart into ammonium and hydroxide. But we also have some cesium hydroxide in there, which can supply 1-to-1 amounts of hydroxide. So the fact that we're after ammonium, which is this, of course, it can only come from this equilibrium. Cesium hydroxide contributes hydroxide, which contributes to the equilibrium amounts of everything there too. So how do we figure out the equilibrium concentration of ammonium, which again can only come from the equilibrium? So we set up the ICE table. So the ICE table, remember, that stands for initial change equilibrium. So we start out with 0.1628 molar ammonia, 0 ammonium, and 0.1362 molar hydroxide. That, of course, again comes from the strong base. Now, we have to have, for this to be equilibrium, we have to have a little bit of ammonium ions. So how do we get that? Well, we consume a little bit of ammonia, because that's where the ammonium comes from, so minus X amount of that, and we form X amount of ammonium ion. And with that, because of the reaction, we also form a little more hydroxide. Okay, so now you remember from setting up ICE tables in your class that the sum of these two, the first two, gives us the equilibrium amount of ammonia. Similarly, the sum of these two gives us the equilibrium amount of ammonium, so 0 plus X equals X. And same thing for the last one, 0.1362 plus X is our equilibrium amount of hydroxide. So we have everything we need to solve this problem. It's just going to be a little hard, at least initially when we look at it, because it looks like this. So you have X inside the parentheses multiplied by an X. So that looks kind of like a quadratic equation. But if you recall how we have done things in past, we note that this X here is probably kind of small compared with 0.1362 and the 0.1628. And if that's true, we can drop the X's out. Then our equation becomes pretty simple. Drop out the X's and you end up with this. Now, of course, and that's a reproduction of what I had there, sorry about that. So that leads us to, when we solve this for X, gives us 2.15 times 10 to the minus 5 molar. It would be the concentration of ammonium ion, X, in this solution at equilibrium. Now, one thing we have to do at the end of this is say, okay, now that we have X, I can put that answer into my answer sheet or wherever I have to put it. But before you do that, you have to go back and check, is this X satisfying this requirement here, that X is small in comparison with these two? And you can see that this is a factor of 10 to the 4th times smaller than either one of these other two numbers here. So therefore, our assumption was a valid assumption to make, and we're done. Hope this helps.